Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be looking at organic chemistry. We are still discussing on alkanes, but today we are going to be looking at the sources of alkanes. And the sources we are going to discuss today are just the natural sources. So we'll look at the sources of alkanes and how, for example, like the fractional distillation, how it happens, and then we are going to see some sample of questions tested on the subtopic. So there are usually three natural sources of alkanes. First, we have natural gas, which usually consists mainly of methane. And then we have crude oil. Crude oil is a mixture of many alkanes. It can be separated into its components by fractional distillation. And the reason why it's possible to separate these different fractions is because they have different boiling points. And then another source is biogas, which contains about 60 to 75% of methane gas. It's also called mushy gas. This biogas is made mainly by the decomposition of organic matter, which produces biogas. So you have heard of the biogas digester that is used to produce electricity, because when these organic substances decompose, they give off methane, which can be used as a source of fuel. Later on, we are going to see the use of this methane in detail. Also, crude oil is naturally occurring. It's a black viscous oil, and the raw material is made up of complex organic hydrocarbon structures that are formed from the living matter that existed million years ago. So the crude oil is we usually get those alkanes from fractional distillation of crude oil. So this is the process. As you can see, the fractional distillation, you can see different fractions depending on the sizes of the carbon atoms. At the bottom, you can see the crude oil is heated to about 350 to 400 degrees Celsius, and until it evaporates and forms a gas. So this gas enters here. Any liquid is drained off as the crude oil gas enters the fractionating column. So at the bottom of the fractionating column, we have the highest temperatures, and at the top, we have the lowest temperatures, as you can see. So as you move on top of the fractional distillation chamber, the temperatures are decreasing gradually. So the long chain hydrocarbons, as you can see, like butane, that has a more than 25 carbon in its chain, is usually condenses fast because long chains have stronger intermolecular forces of attraction. It means they have a higher boiling point. So they usually turn into liquid very quickly because of that high melting point. So as you go up higher, they start condensing and they are collected. So as you go to the shorter hydrocarbons, they usually condense the last one because they have weaker intermolecular forces. The weaker intermolecular forces causes it to have lower boiling point because they do not require a lot of heat to be heated. So as you can see on the lower part of the fractionating column, there is the large molecules of hydrocarbons, and then on the top of the fractionating column, we have the ones that are of low molecular sizes. So we know that hydrocarbons and alkanes specifically have a very high demand. So that's the reason why most of them, like the ones that are high, like the butane that have very long chains, are usually later on. We'll talk about what happens later on as they are cracked to make them to be shorter. So when you look at the fractions, the intensity of the color increases with increase in boiling point. So that means the bitumen that is lower in the fractionating column is very dark. This is boiling point increases with increase in the number of carbon atoms. The higher the number of carbon atoms, the higher the number of covalent bonds. Thus, the first fraction to be distilled is colorless, while the last is distilled is dark black in color. Viscosity also increases with increase in boiling point. So the fraction with low boiling point are less viscous, the ones that are at the top, while the fractions with the highest boiling point are semi-solid. When it comes to inflammability as well, it decreases with increasing boiling point. So it decreases with increasing boiling point. So gaseous fractions are very uh, flammable, the ones that are collected at the top of the fraction with a low amount of carbon atoms, they usually readily catches fire, while the ones that are in solid state, the ones that are low with large carbon atoms, they are almost like non-combustible. So it is important also to note some of the uses of these fractions. So when you go at the bottom of the fraction, we said we have bitumen. Bitumen is used in road tarmacking. And then between 20 and 70, we have lubricating oils that are used for smooth running of engine parts. Are usually added to those engine parts. And then we have 18 to 25, we have the diesel oils that are used for diesel engines. We have light diesel oils that have carbon number 15 to 18 that are used for heavy diesel engines, especially ships. And then we have 19 to 16, that is kerosene, which is used for jet engines and also is used for domestic uses. We have petrol, which is between carbon 5 to 12. It's used for petrol engines. And then we have the gases. Remember at the top we said since they have low molecular mass, meaning they're able to change into gaseous state. So 1 to 4 forms gases, which are usually used for labs and also to be filled in the gas cookers. So another source we said is also cracking of alkanes. So the reason why alkanes are cracked is because there is a very high demand of short chain alkanes from the crude oil. So we get long chains, like for example, bitumen and others that are collected first in the fractionating column, but they do not have variety of uses as you have seen from the uses table. But you notice, like let's say petroleum and gas is very commonly used, there's a very high demand for that. So it is important to be able to break down these large uh, chains of alkanes into small ones, and they're usually broken up in a process called cracking of alkanes. Cracking is done in two ways. We have thermocracking and we have catalytic cracking. So during cracking, short chain alkanes and alkenes and hydrogen gas are produced. Actually, when we discuss the sources of hydrogen, we say one of the sources of hydrogen is the cracking of alkane or cracking of long chain alkanes. So in thermocracking, a refined crude oil fraction containing long chains of alkene is heated to a temperature of 700 degrees Celsius, and then the result mixture is of short chain alkanes and alkenes. And then catalytic cracking is cracking in presence of a catalyst. Remember, these high temperatures of 700 degrees Celsius are so expensive to obtain. So catalytic cracking enables the cracking to be done at a lower temperature of around 450 degrees Celsius. And some of the catalysts that are used are powdered silica, alumina, zeolite. So silica is silicon 4 oxide and alumina is aluminium oxide. So zeolite can also be used as a catalyst. So let's look at a few questions now in regards to what we have discussed. So propane can be changed into methane and ethane as shown in the equation below. So you can see this is propane, it's changed to ethane, methane, and ethane. Name the process undergone by propane. So since you can see on top of the arrow we have high temperature, this cannot be catalytic cracking because it needs to be very specific. So this is thermal cracking. And then the molecular formula of hydrocarbon, C6H14, this tells you that it is hexane. Hydrocarbon can be converted to two other hydrocarbons as shown in the equation. So we have C6H14 forms C2H6 plus X. So first of all, this process of converting is usually called cracking, but we do not know which specifically cracking is it, because you have not been given any information on top of the arrow, but we do have the thermocracking and catalytic. So when we are considering X, we just be doing subtraction. So we can see from reactant we have 6 carbon atoms, product we have 2, so there are remaining 4, so this will be C4. And then hydrogen, from the reactants we have 14, and then from the in the product we have 6, so we need 8 more, so this will be C4H8. So that will be our answer. And then crude oil is a source of many components that contain carbon and hydrogen only. Name the process is to separate the components from crude oil. So it is called fractional distillation. On what two physical properties of the above components does the separation depend? So it depends on different boiling points. And we can talk about miscibility as well. Because we cannot carry out the process of fractional distillation if these substances are immiscible. If they're immiscible, this process is not going to work. It only works for substances that are miscible. And then study the crude oil fractionating column in the diagram and answer the questions that follow. So how would you expect the temperatures to vary from A to E? So basically moving downwards. So the temperatures are high, or we can say temperatures increase from A to A. So we have not been told to explain why, but we know that uh, the ones that are at E is where crude oil has been heated directly. That's why the temperatures are very low. As you move up in the fractionating column, the temperatures decrease gradually, so that at A we have very low temperature. So for each fraction below states at which position it will be collected. So we have C1 to C4, this is going to be at A, and then followed by C4 to C12, which is going to be at B. And then we have C9 to C16, which is going to be C. And then we have C15 to C25, which is going to be D. And then we have C20, which is going to be E. We know F is going to be C25 as we saw and above. So that's the reason why it might not be in this list here. So that's how you answer that question. This brings us to the end. So in the next lesson, we are going to look at now the laboratory preparation of alkanes and see some few questions. So see you in the next lesson.